This is part 4 of the opening lectures on special relativity. Specifically in this video, I cover a classic problem in basic relativity theory that is called the twin paradox. The twin paradox occurs in popular culture, in science fiction, for example, all the time. You probably have seen somewhere along the way an illustration of the twin paradox. A classic example of the twin paradox occurs in the classic 1968 science fiction film, The Planet of the Apes. I'm talking about the first film in the sequence, the one that stars Charlton Heston. I'm not talking about the horrible remake from about 15 years ago with Mark Wahlberg. At any rate, however, I'm sorry if you haven't seen that film. I'm going to go ahead and spoil the plot for you. After all, the film itself is 52 years old. Here's essentially what happens in the film. So in the opening scene of the film, Charlton Heston is an astronaut on a starship, and he's recording a log. And he's talking about how time is elapsing much more slowly for him on the starship than, for example, back on Earth, according to observers in the Earth reference frame. That's correct. Okay, and then he goes to sleep in suspended animation. And then in the next scene of the film, their starship crash lands on this planet. And then all of this stuff happens with apes. And then you get to the very end of the film. The very end of the film, the last scene of the film, is iconic. Charlton Heston and another character are on horseback, and they're riding their horses on a beach. And they round a corner. And then Charlton Heston's character looks off into the distance, and he sees the Statue of Liberty buried in the sand. And then he realizes the following. He realizes that what actually has happened is that his starship has somehow returned to the Earth and has crash landed on Earth. Tens of thousands of years has gone by on the Earth, whereas for him, he has only aged a couple of months over the course of the entire film. That is correct. It is a correct illustration of the twin paradox. The film gets the physics correct. It gets the biology wrong, that's a whole other story, but at least it gets the physics correct. As I said, the film itself is a classic illustration of the twin paradox. Go ahead right now and pause this film, and then go ahead and write down the twin paradox problem from today's lecture examples. Okay, let me go ahead and take you through now the twin paradox. So to summarize what I wrote down for you in the lecture examples, we have the following situation. We have a pair of identical twins. One twin remains on Earth. We're going to call that twin the Earth twin. And then another twin takes a relativistic journey on a starship and then returns. We're going to refer to that twin as the rocket twin. Okay, now, according to the Earth twin, the rocket twin is moving. So the rocket twin's clocks are running slow. So when they come back together, the rocket twin should be younger than the Earth twin. Less time elapses for the rocket twin than for the Earth twin. Now, here is the apparent paradox. As you'll see, there actually is no paradox, but the apparent paradox arises in the following manner. Picture the situation from the rocket twin's point of view. In other words, according to the rocket twin, it's the Earth twin that is moving, so then therefore it's the Earth twin's clocks that are running slow. Less time is elapsing for the Earth twin than for the rocket twin. So then therefore when they come back together, it's the Earth twin that should be younger. Obviously, each twin can't be younger than the other, so then therefore, what is the solution to this apparent paradox? Okay, as I said, there actually is no paradox because there is a solution to this. The solution is to recognize that it is not a symmetrical situation. Think of it, for example, like this. Consider yourselves to be the Earth twin, and I'm the rocket twin. So then basically, the following happens. The rocket twin goes out, and the rocket twin returns. According to you guys, I'm moving, so then therefore my clocks are running slow. I should be younger. According to me, it's you guys that are moving, so then therefore, according to me, it's your clocks that are running slow, therefore you should be younger. Once again, that's a statement of the paradox. However, in terms of motion, I do something that you guys don't do. What is it? Once again, it's not a symmetrical situation. The solution arises in realizing that there are actually 3 reference frames here, not 2. In terms of motion, as I said, I do something that you don't. I accelerate. I turn around and come back. Therefore, there are 3 reference frames here, not 2. The 3 reference frames are as follows. First of all, the Earth reference frame, and then secondly, the outbound journey, and then thirdly, the inbound journey when I return. That then leads us to the solution. Let me outline the solution for you. As I outline the solution for you, the details of actually what happens with decelerating and turning around and accelerating and coming back and blah, 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 none of those details matter. The only thing that does matter is recognizing that there are 3 reference frames. In order to recognize those 3 reference frames, we're going to apply the time dilation equation to the situation. Okay, but let me diagram out the situation for you first. All right, so right here is the Earth. Okay, and then right here is the Earth twin. Okay, this is one reference frame. Okay, now here's our starship. I'm going to just draw a little rocket ship like so. It's moving in this direction with a velocity u. This is going to be the outbound journey. And then right here, for example, is the rocket twin. However, the outbound journey is another reference frame. So what I'm going to do is I'm going to personify it. Here's the easiest way to picture it. Let's say that this rocket ship here has a pilot aboard. We're going to call this guy here the outbound pilot. This is just a means of personifying the reference frame, nothing more. Okay, and then we've got the turnaround point. And as I said, all the details of the turnaround point are totally unimportant. So here's an easy way of picturing things. Let's say that right here, for example, is our outbound rocket, like so. Here's the outbound pilot from a moment ago. And now we've got our 3rd reference frame, which is the inbound journey. So I'm going to just draw another starship. Like so. Moving in this direction with velocity u. And now for this inbound starship, to personify this reference frame, right here is an inbound pilot. And then at just the right moment, if you want to think of it this way, here's the rocket twin like so. He leaps across from one starship to the other, and then ultimately at the end of the example, here's the rocket twin like so. Here's the inbound pilot, and they arrive back at Earth, where the Earth twin is. What we're going to do is we're going to examine different parts of the journey as seen by the 3 different reference frames: the Earth twin, the outbound pilot, and the inbound pilot. The easiest way to examine all of this is to construct a little data table. Copy this down as we go. Like so. Like so. So what we're going to look at are 3 portions here of the journey as seen by the 3 different reference frames. Okay, let's begin by defining the following. Let's say that by definition, the whole trip, according to the Earth twin, takes a total amount of time, capital T. So right off the bat, what we're saying is that the Earth twin ages, capital T. Okay, and then we'll just divide the outbound journey and the inbound journey in half. Like so. So once again, this is all just simply by definition. Okay, now, take a look at the outbound journey as seen by the Earth twin. this value of t over 2. Is the outbound journey as seen by the Earth twin proper or improper? Well, think of it this way. Let's say that I'm the Earth twin, and this right here is the rocket twin for the outbound journey. So then therefore the two events would be the following. We would have the rocket twin leaves, and then the rocket twin jumps across way over there. According to the Earth twin, those two events occurred in different locations. Therefore, it would be an improper time interval. Okay, but now take a look at the outbound journey as seen by the outbound pilot. So now I'm the outbound pilot, and then therefore the outbound journey looks like this. Rocket twin comes aboard, and then the rocket twin leaves. According to me, the outbound pilot, that was a proper time interval because the two events occurred in the same location. Now we can calculate the proper time interval here because we already know what the improper time interval is. It's t over 2. So then therefore the proper time interval is the improper time interval t over 2 multiplied by the radical sign. Like so. Okay, now take a look at the whole trip as seen by the Earth twin. Is the whole trip as seen by the Earth twin proper or improper? Well, now think of it like this. Okay, I'm the Earth twin. Here's what the whole trip looks like. Rocket twin leaves, rocket twin comes back. According to me, the Earth twin, the two events occurred in the same location. Therefore, it's a proper time interval. And now take a look at the whole trip as seen by the outbound pilot. What does the whole trip look like as seen by the outbound pilot? Well, it's a little silly looking. It looks like this. Imagine that I'm the outbound pilot, and then therefore the whole trip looks like this. Rocket twin comes aboard, and then the rocket twin ends up on Earth way over there. So according to me, the outbound pilot, those two events occurred in different locations, therefore it's an improper time interval. Now we can calculate the improper time interval because we already know what the proper time interval is directly above. So using the time dilation equation, the improper time interval is equal to the proper time interval divided by the radical sign. Like so. Okay, and then lastly here for the outbound pilot, we take a look at the inbound journey. Technically it's an improper time interval, but it's actually nothing more than the difference between these two values. And now we examine then what happens according to the inbound pilot, the different portions of the journey. As we'll see, it's basically the same thing here as the second row of this data table. It's just a couple of the terms are switched around. So then here's how we can visualize it. First of all, take a look at the inbound journey as seen by the Earth twin. The inbound journey as seen by the Earth twin looks something like this. I'm the Earth twin. The inbound journey is the rocket twin jumps across way over there, and then he ends up here. According to me, the Earth twin, the two events occurred in different locations, therefore it's an improper time interval. Okay, now what about the inbound journey as seen by the inbound pilot? Well, now that's going to be a proper time interval because think of it like this. Now I'm the inbound pilot. What does the inbound journey look like? Rocket twin comes aboard, and then we're over here on the Earth. According to me, however, the inbound pilot, the two events occurred in the same location. So therefore, that's a proper time interval. Now we can calculate that proper time interval because we know right here what the improper time interval is. It's t over 2. So using the time dilation equation, the proper time interval is t over 2 multiplied by the radical sign. Like so, and that's proper. Okay, and then lastly here, very quickly, once again, the whole trip as seen by the Earth twin, capital T is a proper time interval. Therefore, according to the inbound pilot, it's an improper time interval. It's actually the same thing as this. Like so. And then lastly is the outbound journey as seen by the inbound pilot. Technically, it's an improper time interval, but it's actually nothing more than the difference between these two. Okay, so now I have all parts of the journey as seen by the 3 different reference frames here correctly filled out here in this chart. I haven't said much, however, about the rocket twin, however, in the past few minutes. What does the rocket twin see? Well, I'll give you a hint. The rocket twin sees 2 of the 9 entries here in this data table. What are they? Well, the rocket twin, first of all, sees the outbound journey as seen by the outbound pilot. And then secondly, the inbound journey as seen by the inbound pilot. That's what the rocket twin sees. So then therefore add the 2 together now to get the total amount of time elapsed for the rocket twin. So the rocket twin then therefore ages the following. T over 2 times the radical sign plus T over 2 times the radical sign, which is equal to the following. Like so. So who is younger? Who experiences less time? The rocket twin is younger. Planet of the Apes gets it correct. Tens of thousands of years elapses on the Earth, whereas only a few months elapses then for the rocket twin, Charlton Heston's character. Obviously, less time will elapse for the rocket twin than the Earth twin, and the difference between the 2 depends upon how fast you go, for example, going out and coming back with respect to the Earth. The twin paradox has been directly measured over and over and over the decades. The first time that it was actually directly measured using technology was back as early as the 1950s. In the 1950s, this is when the first atomic clocks were built. Atomic clocks are so precise that they can see time dilation effects even at relatively small speeds. So the Air Force did a test. What they did was they took 2 atomic clocks at an Air Force base and they synchronized them. And then they put one of the atomic clocks on a plane. They flew it across the country and then flew it back. Think of that as the rocket twin, and then the atomic clock that remained on the tarmac at the Air Force base, think of that as the Earth twin. And sure enough, the rocket twin, that atomic clock, aged, if you will, less than the Earth twin, that atomic clock that remained on the tarmac. The difference between the 2, of course, was just a fraction of a second, billionths of a second, if that, but it was directly measurable. As I said earlier, the twin paradox pops up in popular culture, science fiction all of the time. Besides the Planet of the Apes from 1968, for those of you that read science fiction, I encourage you to try a short story called Remembering Siri. This is by Dan Simmons. This is for those of you that have a romantic heart. And then I also encourage you to read the 2nd book in the Ender series, that is The Secrets of the Dead, I think it's called, Secret of the Dead. At any rate, however, that particular book, that also is a nice classic illustration of the twin paradox. Today's shirt was immortal.